Compact, computational optimization and automated modular design of planetary actuators. Robotic actuators are one of the most critical mechanical components of a robot. Precision manufactured metal actuators offer high performance, but there is increasing interest in 3D printed actuators due to their ability to enable rapid prototyping, lower cost, and faster design iterations. However, robotic actuators are still commonly designed using heuristics and designer intuition, rather than systematically identifying the optimal design for given joint requirements. In addition, actuator design still requires significant manual effort, and the automation of robotic actuator design remains largely unexplored. We address these problems in this work. We introduce Compact Framework. This framework finds optimal gearbox parameters for a given motor and gearbox type. It also generates automated parametric CAD for the optimized actuator. The generated CAD model can be directly 3D printed to fabricate the actuator, without requiring any manual intervention. This flowchart illustrates the overall workflow of the Compact Framework. The framework takes motor specifications, gearbox type, and the gear ratio, or a gear ratio range, as inputs. The optimizer block takes these inputs and computes the optimal gearbox design. The optimization variables include the number of teeth of each gear, the gear module, and the number of planet gears. The optimization is subject to several constraints, including gear ratio constraints, geometric constraints, meshing constraints, interference avoidance constraints, maximum gearbox diameter constraints, and other additional design constraints. The cost function aims to minimize the actuator mass and width, while maximizing the gearbox efficiency. The mass, width, and efficiency of the actuator are computed using the actuator model. The gearbox is optimized using a brute force optimization algorithm, which determines the optimal design parameters. These optimized parameters, together with the fixed design parameters, are used to compute the dependent design parameters, which are written to a parametric text file. This file automatically updates the parametric CAD model, resulting in an automatically generated optimized CAD design of the actuator. The generated CAD model can then be directly 3D printed to fabricate the actuator. The Compact Framework code is available at the link shown on the screen. You can follow the README to set it up in your workspace. Let's look at an example. We optimize and generate the CAD for an actuator using the MAD M6C12 motor, a CPG gearbox, and a 13:1 gear ratio. We run the command, and the optimization takes about 12 seconds. After the optimization, you can see the time taken, the optimal design parameters, and the final gear ratio. Next, we open the automated CAD model and rebuild it. The CAD is then updated automatically, and the parts can be directly 3D printed to fabricate the actuator. We perform a simulation study using the Compact Framework. The setup is shown on the screen. This study evaluates the accuracy of the actuator mass model and provides insights for selecting gearbox types and parameters for a given motor. We compare the actuator mass predicted by the model with the mass obtained from the automated SolidWorks CAD. The model mass closely matches the SolidWorks CAD mass, see graph. We also try to find which gearbox type and what parameters are optimal in different gear ratio ranges for the motor MAD M6C12. The insights are given on the screen. Pause the video to read them. We generated multiple actuator designs using different motors, gear ratios, and gearbox types. We fabricated 2 optimal actuator prototypes. The first is an SSPG actuator with an MN8014 motor with a 7.2:1 gear ratio, and the second is a CPG actuator with a MAD M6C12 motor with a 14:1 gear ratio. We then evaluated these actuators through 3 experiments: a power efficiency test, a no-load backlash test, and a transmission stiffness test. These are the results of the power efficiency tests. The predicted efficiencies are 96% for SSPG and 93.8% for CPG, while the experimental efficiencies are lower, 60 to 80% for SSPG and 60% for CPG, mainly due to 3D printing limitations and friction. Still, SSPG shows higher efficiency than CPG, consistent with theory. Results of the no-load backlash test: the CPG shows about 2.6 degrees of backlash, while the SSPG shows a much lower backlash of about 0.59 degrees. Results of transmission stiffness test. The SSPG actuator shows a stiffness of about 242.7 Newton meters per radian, while the CPG actuator shows about 201.6 Newton meters per radian. This means the SSPG is stiffer than the CPG, mainly due to its larger planet diameter and higher effective contact ratio. Thank you.